Similar triangles are exactly the same shape, but they are different size. But when we talk about different size, we're talking about them being in proportion to each other, the sides. And we'll get into that a little bit further on in this exercise. Now, what do we know? We know that corresponding angles will be equal and corresponding sides are in the same ratio. That's an interesting point, are in the same ratio. So let's talk about corresponding to start off with. Corresponding means have to be in exactly the same spot. And if they're angles, they have to be exactly the same angle. But if they're sides, they have to all be in proportion or ratio to each other. Now, when we talk about two similar triangles, we use this symbol here. Remember, congruent was 3 lines, but they were horizontal. For similar, it's 3 lines and they're vertical, slightly on a slant. Or you can use this little symbol here, which looks like an approximate, but that's telling us that those two triangles are similar. Now, when we were talking about congruent triangles, they were the same shape and same size, and they actually had their set of rules to be able to work out whether or not two triangles were congruent. Well, it's no different for similar triangles. We have 4 rules here which we will use in order to judge whether or not two triangles are similar. So the first rule that we're looking at is when all of the corresponding angles are equal. A. Corresponding, so this angle corresponds to this one. This angle in exactly the same spot as this one, and this angle corresponds to that one. You can see the triangles aren't the same size, but they don't have to be the same size for similar triangles. Now the next rule, which is side, 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 all 3 sides have to be in ratio. This is where it becomes interesting. So let's have a look at the corresponding sides. This side corresponds to this one. What have we done to get from the smaller one to the bigger one? We've times by 2. This one corresponds to this one. What have we done to get from the smaller to the bigger? We have times by 2. And the last side, last pair of corresponding, 3 to 6, times by 2. So all of those sides to get from the smaller to the larger, we have times by 2. We actually call that the scale factor. That second triangle, the lengths are 2 times bigger than in the smaller one. And it needs to be the case that you need to be multiplying all the sides in the smaller one by exactly the same value to get to the bigger triangle lengths. And that's why we call them similar triangles. The third rule that we can use is called side angle side. Now, what does that mean for similar triangles? Well, it means that the corresponding angles have to be the same, so they must be the same angle, and the corresponding sides have to be in ratio. Remember we talked about in ratio before? In ratio means that to go from that one, which corresponds to that one, we are timesing by 2, and to go from that one to this one over here, we're also timesing by 2. So the 2 sides are in ratio. The 2 sides have to be on either side of the angle, so that is the included side. So it must be side, angle, side. 2 sides in ratio, angles the same. Our last rule that we can use is the right-hand side rule. So obviously here we're dealing with 90-degree triangles, right-angle triangles. So what does this rule say we have to have? Well, it says in a right-angle triangle, the hypotenuse, which is this one and this one, need to be in the same ratio. So what have I done to get from the 4 to get to the 8? I've times by 2. They need to be in ratio to a pair of corresponding sides in either triangle. So this one actually corresponds to this one up here. All right. And so what have I got from 3 to get to 6? I'm timesing by 2. So as long as you've got the hypotenuse and one other pair of corresponding sides in ratio in a 90-degree triangle, then those two triangles will also be considered to be similar. Scale factor is a term that's going to be more widely used as you go into year 11 and year 12. And so we just previously talked about this scale factor. It's telling you how much bigger the side lengths are in one triangle compared to the smaller one. And often we use the letter K for scale factor. So let's have a look at this first example, and the question is asking us to decide whether the pairs of triangles are similar and give reasons. Now, hopefully most of us could work out here that all of the angles in both the triangles are the same, because although we've only got 2, remember all the angles in a triangle add up to 180. So we've got all 3 angles being the same. It must be angle, angle, angle. However, the question says give reasons. So how do we write our answer? Well, this is the way we need to set it out. We know that triangle, or angle, beg your pardon, BAC is equal to angle EDF. Remember, angle BAC, we're looking at the angle on A, which is 70 degrees, and angle EDF, we're looking at the angle on the D. It's always the middle letter. Okay, that's also 70 degrees. That's why those two equal each other. What else do we know? We know that now angle ABC, so the angle on B, and the angle on E, so DEF, are equal to each other. And we also know that angle ACB is equal to angle DFE. So remember, the letter in the middle tells you where the angle is. So for that last one, ACB, we're talking about the angle on C. All right, and for the second triangle there, we're talking about the angle on F. Those two equal each other. So therefore we can say that triangle ABC, is similar to triangle DEF, and the reason is angle, angle, angle. With this second example, we can see that we don't have any of the angles, but we do have all of the sides. So what we need to decide is whether or not those sides are in ratio to each other. Now, sometimes the triangles aren't drawn exactly the right way. And for this one, what I need to do is just reverse that second triangle. So let's have a look at what it should look like. Now that I've reversed the triangle, you can see that to get from 7 to 14, we times by 2. To get from 5 across to 10, we times by 2. To get from 8 across to 16, we times by 2. So what have we got here? We've got DE divided by AB, EF divided by BC, DF divided by AC. And remember, DF is from D to F. These are all side lengths. The bigger ones on top, the bigger triangle over the smaller, and it is 2. So that therefore it is side, side, side. So we should probably also write here that therefore triangle ABC is similar to triangle DEF. So that would be all the working out that's required. So looking at the third one here, on close inspection, it looks like it could be side, angle, side, because the two angles are the same. Let's check to see if the corresponding side lengths are in ratio. So this side length corresponds to this one, and that one would have to correspond to that one. So remember, it is the bigger triangle divided by the smaller. So let's do that. We've got DE, which is the bigger triangle, divided by the corresponding side on the smaller one, which is AB. What does that give us? Well, that's 3 over 2, which is 1.5. What about the other corresponding sides? Or are they? Let's check it out. So it goes from D to F, remember, bigger triangle, D to F, over, what's the corresponding side on the smaller one? It is A to C, and we've got 4.5 over what? Over 3, and that's also equal 1.5. What that tells us is that to go from the side lengths in the smaller to the bigger one, we're timesing by 1.5. And the other bit of information we know there is that angle BAC is equal to angle EDF. They're both 80 degrees. So therefore, because we have two sides in ratio and the included angle being the same, then we can say they are similar triangles using the rule side, angle, side. Finally, our last pair of triangles here. Are they similar? Well, by process of elimination, these two have got 90-degree angles. So it looks like it could be the right-hand side rule. We've both got 90 degrees. So we've got angle BAC is equal to what? Angle EDF. Again, they're both 90 degrees. Now for the right-hand side rule, the hypotenuse and one other pair of corresponding have to be in ratio. Well, here is the hypotenuse. All right, so let's check that out. The hypotenuse there in the bigger one is from E to F. What is the hypotenuse in the smaller one? It is from B to C. And what do we get when we work that out? 16.5 over 11. And we divide that up in our calculator and we get 1.5. Well, let's check out that other pair of corresponding sides. And what is your other pair of corresponding sides? It is this one and this one. Now remember, they're not sitting the right way, but if I was to redraw those, then perhaps they might be. So what do I get when I do that? I've got side D to E, bigger triangle, divided by side A to B. D to E is 7.5. And what is A to B? That is 5. Divide that up and you get 1.5. So they are the same. So the sides are in ratio. So because the sides are in ratio, okay, the sides are in ratio, we can say that they are similar triangles. So therefore, we have triangle ABC is similar to triangle DEF, and the rule that I used was the right-hand side rule. I probably should have done the same thing for the question up here. I should have said triangle ABC is similar to triangle DEF, and of course the rule there was SAS. This example is slightly different. We're told that if the given pair of triangles are known to be similar, so they are similar, we don't have to prove they are, find the value of x. Well, they are similar, which means their sides are in ratio to each other. So let's take a look at a pair of corresponding sides that we already know. The ones that we already know are this one and this one. Now to go from the smaller to the bigger, I'm timesing by 2. How do I usually work out that scale factor? I say the bigger triangle, which in this case was DE, over the corresponding side in the smaller, which is AB. And so that's 4 divided by 2, which is 2. Now, you probably could have told me, well, that's pretty simple. To get from 2 to 4, you've got to times by 2. Sometimes it's a little bit trickier to work out. So that's a good way of doing it all the time. So the side in the bigger triangle divided by the corresponding side in the smaller triangle. So now we know that, well, our scale factor is 2. You've got to times by 2 all the time. So in our triangle here, in the smaller one, we have side 3. A to C is 3. So therefore, it would make sense that in order to get from there to there, I would have to times by 2. So x is equal to 3 times 2, which is equal to 6. And we could only use that method because those two triangles were similar. Now, my last example here is pretty interesting and pretty complicated. So if you can get this one, you can get anything. Hopefully, what you can now see in this one is that we have two triangles. And they are actually similar triangles. How do we know that? Well, let's have a really good look at it. This angle here and this angle here, they're both made with the vertical, and that line is the same angle going downwards, so they must be the same. And we've got 90-degree angle there and a 90-degree angle there, and of course they both share this angle here. So if I looked at those two triangles, I've got my big one and I've got my smaller one. Let's fill in the information that we know about them. So in the bigger one, it is 3.6. There's my right angle. I know from there to there is 6.6. Okay, in my smaller one, there's my right angle. That's x. What else do I know? I know that that is 1.2. And of course, I know that this angle is the same as this one. And this one is the same as this one. So I want to find x. How do I go about doing it? Let's look for our corresponding sides first. Because we know that they are similar triangles, we know the sides are going to be in ratio. So this one and this one are corresponding. And this one and this one are corresponding. So let's find our scale factor. Bigger side length divided by the smaller one. They have to be the corresponding sides. So 3.6 is in the bigger triangle, and the corresponding side in the smaller one is 1.2. And when we divide that up, we get 3. That's telling us that the sides in the bigger triangle, you would have to times by 3 to get them. If I was going back the other way, if I was going back to the smaller one, then I would have to divide by 3. So what does that tell us now? Well, 6.6 corresponds to x. How do I get x? Well, if I times x by 3, I get 6.6. But remember, we could do it that way. You get 3 times x is equal to 6.6. I want to get x by itself, so I need to divide by 3. And I get x is equal to 2.2. So again, we could only use that information because we knew that they were similar triangles. We cannot use that method otherwise.